AGI, it's almost here. If you haven't read your Nick Bostrom, it's over. You got to be listening to Yudkowsky on the reg, my man. Because listen, otherwise you're not going to make it. Not without the help of me and people like myself. All right? Don't worry. We'll get you through this. It's going to be all right. But we're going to have to learn how to do MLAI. We got to convince these bots that we know what we're talking about, that we're their friends. All right? That's my proposition here. All right. So today we're going to be talking about softmaxing. All right. So to get started, why do we need a softmax? What am I even talking about here? Well, a softmax it's literally just like a mathematical equation to normalize outputs. That sounds, what does that even mean? Don't worry, we'll get to it. All right. So let's say we have a simple neural net set up like so. Let's say we have 3 classes, and our 3 classes are going to be good robot, bad robot, and Skittles. We have a neural net, we're using like neural regression or something, and we want to decide, all right, is a robot I feed into this, is it good, is it bad, or is it like I'm just showing it a pack of Skittles, all right? Okay, so let's say we have this evil robot, right? Pretty clearly evil for, our human understanding, right? We can see it's got laser eyes, etc., up to no good. Let's say we feed it into our neural net. The output we're going to get, if we're using most ML systems, aren't initially going to be any kind of easy to understand value. We're not going to get a probability distribution, right? Where we have like, oh, it's a 45% chance it's good, a 35% chance it's bad, and then a 20% chance it's Skittles. That's not initially what we're going to get. No, it's going to look quite whack. We're going to get something more along the lines of maybe we get like -7, 15, -103. These are what our outputs are going to look like. Now, generally, we can kind of say, right, that like increased numerical values correspond to higher probabilities, but we want to actually quantify this and get a probability distribution that sums to 1, right? We want those actual numerical probabilities that we can actually use and evaluate very quickly as humans. So how do we do that? Well, that's where the softmax comes in. Here is our softmax function itself. Basically, each of these scalar values predicted by our neural net are going to be converted to probabilities that sum to 1. So we now have a good probability distribution that we can use to, actually get a good understanding of, our model's performance. What does it estimate the probability that this is a bad robot as opposed to a good robot or a pack of Skittles? And let's kind of dive in and understand what this actually does. The numerator of this function is basically designed to take the exponential of our given output. So we take like e to the -7, e to the 15th, e to the -103rd. Then on the bottom, our denominator is basically just normalizing by the sums of the exponents of everything in our output set. Let's say we're doing good robot, so e to the -7 divided by e to the -7 plus e to the 15 plus e to the 103. And what this gives us is the numerator. By taking our exponent, we get rid of any chance that we're going to have negative probabilities, right? It forces the output to be positive and makes sure that it's not negative or 0 or anything else weird. And then for the denominator, what it basically does is it normalizes that now positive integer value and forces it into a probability by dividing it by the sum of all of our different scalars in our input set. For kind of a quick example, let's say we want our probability that it's a bad robot, right? We want to see how good our model is. Well, the actual softmax of that is going to be e to the 15th over e to the 15th plus e to the -7 plus e to the -103. Which, after crunching the numbers, actually comes out to about 0.99 repeating. So our model would be doing pretty good in this instance. We've got, we converted our number of 15, which how do you even really quantify that, to a 99% chance after running our model that it's a bad robot, which makes sense given our input. And this is useful for all sorts of ML applications when we're basically trying to take numerical outputs for classes, especially in the field of categorization, and we're trying to assign and enforce that into a type of probability distribution so we can analyze it that way in a much more human readable format. Anyway, that's the Softmax. If you know this, you know how to spot bad robots and avoid the soon-to-be robot revolution. Thanks for tuning in. Give us a like and a subscribe.